Hi everyone, hope everybody's doing well. It's been quite a while since I last posted anything, but there hasn't been really much going on. The only, let's say, updates that I've seen have been these purple welder versions come out, and there have been, I think, a couple of revisions, and that's why I decided to do this short kind of, we'll see how long it will be, video on the newer K100. Call it newer, but it's actually been out for a while. But this one that I have needs a mod. So I have received several questions, and I did post something about the mod in the community section. This is the one I received. The only thing I did here, I've never actually tried this one yet. I just soldered on the XT60 connector, which I find pretty handy if you're using LiPo batteries. It's, you know, a direct connection, pretty handy, and it will shorten your cable. So instead of having like a double cable to power the battery, if you are using a LiPo with a connection here and a classical connector, you connect directly to the PCB. So yeah, you have a slightly lower resistance, and that will give you a higher current peak when you're welding. So this board, which I ordered, is actually the bare bone, because you can order various versions, the one with the whole kit, the cables and everything. As I have several cables, I just decided to order the bare bone board, let's say. It doesn't come with any screws or anything, it just has the board and that's it. And it has this, comes in this little box. Here's written K100 and I don't know, some reference here or some order or whatever. It has this leaflet with this let's say brief instructions, and yeah, you can see that there are a couple of versions: the one with the battery, the one with the LiPo, which they corrected assembly, and this is the one that you know, they gave it to you, by the way, without the connector. This connector is not provided. You can buy it separately on AliExpress. They're cheap. You just buy a bag of them and keep them handy, because more or less they always use them. And it's the, let's say, bare bone version. They call it the 12 tube here, because you can actually put another 6 FETs on the back on this side, which I have not wired. I don't think they're, I mean, for my purposes, are not necessary. And to be honest, if you have 6 of them which are balanced, you know, as I described in my previous videos. By the way, if this is the first time you're watching this, please check the playlist and look at the frequently asked questions video, where I explain the importance of having matched FETs and what it means and how it can influence everything, and why people have these different results with their let's say cheap mini spot welders. Some are really satisfied, some they blow up in your face a second time. So you know, it's all due to this, the matching of the FETs, the protection, which, yeah, as you can see, there are no transient protection devices here. There should be some TVS diodes near the FETs, but yeah, well, you know, it's a cheap device, so you can't expect it to be perfect. I explain this and go into detail, so please check out the previous videos. There are a lot of them, apart from the frequently asked questions one. It's in the playlist, and they cover all of this, the reasoning and why it's necessary. Briefly speaking, this is just a switch. It's a controlled switch where you can adjust the time and on time, and that's all it does. It just simply dumps the battery power onto two, you know, contact points here. The current passing through will weld the strip, and it does that by mere resistance. So this is all covered by in my previous videos, especially the frequently asked questions one. So now this board specifically, this revision does not have the decoupling for the opto here. This is the optocoupler that triggers the gates of all these FETs, and if you look at the schematic, well, if you look at the PCB, you will see that there is a trace going from the output. This is the output side, and it goes to the FETs. Now, this side here, I'm checking on the camera. Okay, you see there's a trace going up here, and pin 1 of all these FETs is the gate, and it's the first pin. Maybe it's easier to see it on the back because there are no FETs. So if you see the first pin here, you see this is the only pin that is not connected to the others. That's pin 1. This pin here is the gate, and they're all in parallel. So they have a via 1, 2, 3, 4, 5, 6, and they go to this side because they're connected together. So, you know, pin 1 over here, turn it around, and there is pin 1 here. You see? A little bit closer. And this pin here is the one that is connected to the output. You can verify this using a tester. So just take a tester in ohms. This is also good if you check this once you've done any mods, because you might inadvertently have shorted it out with a drain or with a source here. So pin 1 here, if you touch pin 1 on this side, pin 1, pin 1, pin 1, and the others aren't connected. So it's all these pin 1s, and you can do this on the back too. Pin 1, pin 1, pin 1. They're all in parallel. Now, I won't go into super detail of paralleling them all, but let's say that they should have an impedance matching resistor, let's say in series. But if you check the tester here, you see it's like one. It's a dead short. So these are all in parallel, and this is the output that goes from the opto to the gates. Don't know if you can see. There is about a 10 ohm. You can see that? I don't know if you can see it. It's a 10 ohm value, and that's a little resistor that's put in series. The gates are all in parallel, and every gate is like a small capacitor. So the more gates in parallel you have, the bigger capacitance you have, because you have to add it when you put them in parallel. And this creates an enormous stress on the opto. Suffice to say that this opto is not developed to drive any kind of FET, because it doesn't have a very fast switching time, and it doesn't have the power. This little junction that's here doesn't have the power to drive properly these FETs. It works, yes, but it doesn't work efficiently. You would need a proper FET driver. I've talked about this several times, but because of cost purposes, production, you know, they want to keep everything cheap. This is what you get. So when you do decide to double the FETs and put 12 FETs, this device here will have double the amount of current it needs to push to drive the gates and turn them on. This means that it will be twice as slow, because you don't change this. You're not changing also the opto. You're just adding more load to it. And so you're gonna get let's say, you're going to be stressing the FETs more, especially if you're driving several hundred amps over the design of this, let's say, little board. So today what we should be doing is, what we will be doing, is to decouple this opto from the 12 volts of the board. I mean, coming from the battery. That's what I meant, you know, from the battery, because the battery here is connected to these contacts, or of course on this plug, and the opto here is driven by the MCU, which is this little integrated circuit here. One pin comes out, just turns on the LED. There's a little LED here, and it's galvanically isolated, meaning there is no contact between this side and this side, electrical in electrical sense. And the base of this transistor is turned on by the infrared light of this little LED that's inside, and this is simply turning on. So it starts conducting, and it brings the plus voltage, which is on this rail. If you check this bottom side, this plus side comes directly to this plus side. In fact, they are connected. And there's a little trace that from here runs up and goes to the opto. As you can see, this little trace here. So let's say you have a, let's say, not so performing power source. Maybe your LiPo isn't perfect, or you're using 3S LiPo packs here, and the minimum suggested is 5,000 milliamp per hour. So stick to that value, and they have to be at least 50C, meaning that they have to deliver at least 50 times the amount of their rated nominal current to be able to perform correctly and weld. So let's say the battery, I don't know, maybe it has one element, or one of the two elements, or the three elements is not performing well. So when you do dump 200 amps or more, usually it's over 400, on the weld, the voltage is going to drop. And it's going to drop pretty much. It can drop even 6-7 volts. It's a lot. It can drop more, over 50% of the battery rated voltage, because voltage drop is expected. And that's how the weld works, meaning that you have a very small resistance between the weld, the FET drain source resistance, the cables, and the internal resistance of the battery. All this is explained in my frequently asked questions video, by the way. And so there is an expected voltage drop, and this translates to power and heat, and that's how the weld occurs. But if this voltage drop is extreme, meaning that it drops too much, let's say over 40% of the rated voltage, what happens is that this little opto, the voltage is dropping, because, you know, this is the voltage coming from the battery. And so automatically the voltage that is going to the gates is also dropping. And that's not good, because these FETs are saturated and well on above, if you want to be on the safe side, 5 to 6 volts. They do turn on, they start turning on at a lower voltage, but you can't stay around the so-called Miller plateau. You have to surpass it quickly, so that you saturate these little gate capacitances, and you turn the FET fully on. Now, once the FET is fully on, it is really not so delicate. These withstand several hundred amps, so that's not the problem. The problem is reaching that on state. And the speed at which you reach that on state is very important, because that's how you blow a FET. If it's not fast enough, or if the gate is not saturated enough, because there's a voltage dip during the weld, then that's how you blow a FET. So it's not just transient, it's also to guarantee that the gate is fully saturated. So to avoid that, we decouple this, meaning that you separate the positive from the opto by inserting a capacitor. This capacitor keeps this voltage, let's say, constant for a brief amount of time, or an amount of time which is necessary for the weld to end. Usually it's, 5, 10 milliseconds, 15. It's a pretty brief amount of time. And so in this version, the older purple, or let's say the other version, which is, I don't know what it's called, let's say the purple one, which has only 5 FETs, my previous mod was exactly the same. You cut the positive trace and you insert a capacitor, like in this case there's I think 100 microfarad here or something like that, with a little series resistor, very low, 10 ohms, 20 ohms, so that, you know, every time you power it, the resistor and the diode, which is in series, this is a little series circuit, charges this capacitor. There is a diode, of course, because you don't want to be discharging the capacitor if the voltage drops, right? You want to decouple it, meaning that if the voltage drops, the capacitor has to be isolated from the power source, and it does that through a diode. So when the voltage drops, the diode stops conducting, there is no reverse bleeding of the voltage back to the power source, and the capacitor can successfully decouple and power the opto. And that's what the diode is for. However, as this capacitor, it's true that this is a small capacitor, but to stay on the safe side, what happens is that when the capacitor is discharged and you do not have a series resistor, and you connect the diode directly to the positive, every time you power the spot welder and this capacitor is discharged, you're going to get a very high peak of current going through the diode to the capacitor to charge it. And you can see that often when you connect, you know, remote control or controllers or speed controllers, you get this little spark, and that's the capacitor charging. On big speed controllers where they have very big capacitors, you need a special plug, which you could also use here, which has a so-called anti-spark mechanism. And the plug, which you use to plug in, it actually has 2 contacts on the positive side. The first one that touches goes through a resistor. Now that, as soon as you connect it, will charge the capacitors to a high enough voltage so that when the whole plug is inserted, meaning that it's contacting completely, bypassing that circuit, you won't get any spark. And that saves also, you know, your plug, because every time you do get a spark, it makes a little hole. You don't see it, but on the long run, it does ruin plugs, especially if you have a high amount of current going through and the capacitors are big. This is not the case, of course. We have a very small capacitor, so if you put a large enough diode, you would be able to, let's say, not use a resistor, but it's never nice. I mean, if you're doing the mod, do it properly. So that's all you need, just a few ohms. You can even put like a 5 ohms resistor or 20. The only thing that changes is the charge time. But you know, every time you do weld, time between one weld and another is usually a few seconds, and that's more than enough for the capacitor, the small capacitor, to charge back up again to the battery voltage with even a 20 ohm or 40 ohm resistor in series. So that's the decoupling concept. Back to here, we will be cutting this trace. So this trace will be isolated, and then actually this mod, which has been applied to the more recent versions of these KEKK, if you check, what they did is they used the top side of this part here, and they connected the positive of this leg through a trace which goes on the top side here and down to this 470 microfarad decoupling capacitor. This is actually the decoupling capacitor which is used for the logic, and it's pretty big because 470 microfarads is more than sufficient to also decouple this. So we're going to be using this capacitor and not be adding one here. Plus there is also a diode here already in series, it's this one here. Of course it needs one, because otherwise it wouldn't be decoupling the electronics here, and the regulator, there's a little 3.3 volt regulator, which is this little IC here. So you get the positive side goes through the diode, the output of the capacitor is decoupled, and you have this area which is decoupled from the power source. So we're going to be stealing, let's say, the output of this capacitor and wiring it directly onto the input side of the opto here. Input meaning the junction. This is actually the trigger part, right? So this is basically the mod. It's not too difficult, but I will just show you the wiring here. This one goes directly to this leg here. It's I don't know if you can see the, I think it's better like this, maybe. Okay. This is the positive side, this is the other side, and this goes here, and it's like 3, 2, 1. Well, it's a little bit slow, this tester, but it works fine. And then the output is on this side, and this side goes to the gates, which is here. Every single gate has it. There should be a 10 ohm resistor in series, which we checked. And there it is, 10 ohms. So, cut here, wire this. You can solder something directly on the leg here, or scrape a pad here, as you wish. I will do this wiring. Put a wire along the top side here, and then connect it to the output of the decoupling capacitor here. And let's see if you can check here. This is the negative side, and the positive side is on this side. So let me check. This is the input of the regulator. This is like here, and this is the positive. And the output is on this side. This should be the negative, which is, let me check. Let's see, and it's here. The center pin of this regulator is the negative. So you have the input, ground, and this is the output. This output then goes to the ICs. Oops, my tester turned off. Okay, so this side here goes to power devices here, probably even here. This is a positive side here. This is the plus. This is, I think, a Nuvoton IC MCU. They use these cheaper versions. They're kind of like clones, and they are all used on all of these program spot welders. It's a very common IC that they use there to make these devices. So this side is the output, which we have to wire to this pin here after we've cut this. So we can use a, I don't know, like a little cutter, and find my other glasses here, and go and cut that trace. See if I can cut it without knocking the camera over. Okay. I'm cutting it here because I guess it's more visible. Doesn't matter where you cut it as long as you do. You can also use a small Dremel. And then you can go ahead and verify if it's being cut or not. Let's check. Okay, there's no more continuity between this and this, so it's being cut. Yeah. So now that this has been isolated here, can go ahead and just simply wire a piece of wire from here. Let me use my pointer. From this leg here, if it's clearly visible, and you can wire it, route it around this side if you want, keeping it on the top, and then connect it to the output here of this diode or this pad here. I think maybe the pad of the diode is more accessible. So you just need a piece of wire for this mod, that's all. You don't need any extra components or resistors or anything. We're just gonna, let's say, use the circuit as it is. And if you've noticed, they do not have any resistor in series between the diode and the capacitor charge. So they just dump the full load directly. All the current will go through this diode. Now, due to the losses, the diode will probably, it's a rather big diode. I think this can handle an amp or so. I need to check, maybe more. Anyhow, it can handle it. The capacitor is not enormous, so yeah, it's stress. But to be honest, they should be putting in the series here a few ohms resistor. That's, that's what they should be doing, but okay. And if you follow this trace, it goes directly to the positive pad here. So there is nothing in between here. The positive comes through diode and goes to the capacitor, decoupling capacitor. Then you have the negative here. The output of this goes to the regulator, and that's that. There's a little capacitor here for this, decoupling also for the regulator, close to the regulator. That's normal. Then you have another couple of capacitors here, and then you have these button switches which are going through a this is a voltage divider ladder, and the output of this goes to one input. So basically they're using one pin of the MCU, and based on what you press, you are putting a voltage, different voltage every time you press one of these buttons on that pin, and that pin is actually a analog to digital converter. They have this the pins can be programmed that way. So based on the voltage it detects, it knows which button you press. So maybe it's like 0.3 volts, 0.6 volts, and 0.9 volts. I know, I'm just saying. And so based on the voltage that it sees when you're pressing it, it knows that you've pressed that button. This is a cheap and easy way to, let's say, use less input pins. You could have one input pin per button, but yeah, it's kind of a waste. And maybe they even do this. I actually haven't checked, to be honest, how this one. The other one was working with one input. This one I haven't actually traced all the traces, but I see all these little resistors here, so it makes me think they also have these 1, 2, 3, 4 little transistors here, which probably will be driving something. Yeah, I will try to maybe trace this out, but that's besides the point of this small short video, which was just to decouple this from the positive side. Okay, so we've cut the trace, and now we'll find a little piece of wire. It can be a red wire or yellow, it doesn't matter. Let me see. I have a small, but this is too short. Yeah, need something longer. So let's use a red wire. Cut a piece here. Okay, these are silicone wires, so they are actually heat resistant. And we will need to measure it from here, making its way to here. So basically you need this much. Okay, cut this up. Let's see. If I can route it this way. Yeah, why not? You could also route it the other way from the top, but I think from the bottom it may be more tidy. You get some solder. Okay, and let's just tin this a little bit so it will solder easier. Okay. So I think you can solder this, cut it just slightly shorter, solder it this side, if I can see through the harness here because I have the tripod in my face. Okay, so soldered, okay, wire it this way, and then just stick it on this side here. So I'm gonna cut this a little bit shorter. Should be okay. Okay, and see if I can reach the diode output on this end. Okay. Could be using a set of tweezers here, which wouldn't be a bad idea. So let me get my tweezers. Okay. That should do it there. See if I can reach this out. Okay. Should look okay. Actually, could be soldered the other way around, to be honest. So it would be keeping it tucked under. Okay, I mean, looks okay. Now there will be a lot of current going through this rail here because you have the drain and the source here. And so this track, which is parallel to this, let's say, negative power line, you can be inducing some interference, but this is on the, let's say, on the drives, on the output side, so it's, I'd say, pretty safe. It's not, shouldn't be a big disturbance. I mean, the current here will be high, and here it will be rather low. Okay. And the mod that I've seen that they've done is actually the same. It follows the same path. Alternatively, you could go under here and to the top. But okay, I doubt that that will be a major issue. So at this point, this version has been modded. The output of the here, the positive of the battery has been decoupled. It's not making contact here anymore. The output here is reaching the output side, the drive side, let's say, of the opto. And if you connect your battery here, you will have full voltage here decoupled through this capacitor. And so this should be protecting your gates better. And if you have a defective or low performance power source, the drive side won't be affected by it. Of course, your welds won't be that great because if the battery doesn't deliver that current, you're gonna be, you'll notice it. Particularly if you are insisting on increasing the time above 10 to 15 milliseconds. I mean, based on my experience and the 0.12 millimeter strips which I use, I've never gone past 0.15. I mean, I have some 0.20, but it's way too much for what I need. I usually weld on 10 milliseconds. So the setting is 10. And 10 milliseconds for me, based on with my batteries, I have a couple of LiPo packs and also a small AGM battery, which I haven't been using for a while. I could always get 10 to 15 milliseconds, do decent welds, and they you know, they won't strip off, or just, you know, they will actually puncture if you try to rip the strip off. So that means it's welded correctly. To test this, actually, we could. By the way, this is a. I didn't mention this, but if you unclip these plastic clips, you will see what the display is actually like, and that was an alternative to the wiring. Push this through and push this one through too. You can remove this kind of cover, and you will see that under here there are just a series of LEDs. These are the LEDs that are making up the display. So for them it was cheaper to actually produce this little plastic prism or whatever, you know, light pipe display, call it as you wish. And they probably sell these already pre-made. You just need to fit your LEDs in these slots. So you have this on your PCB design, and you solder and you map the LEDs in this configuration. And it's also, you know, an alternative way, because you can buy these LED displays which are ready-made, but they usually don't have customizable characters like you have here on the side, and they're more expensive. Instead, you buy this, which is just a piece of plastic with some translucent material here, and then you just buy the LEDs. These LEDs are extremely cheap. I mean, they're like 2, 4. There are 5 on each side, so that's 10, plus the 7 segment, so it's 7, 14, 21. So you have like 31 mini LEDs, and it's like a few cents. It's nothing. Instead, if you buy the display like this is a proper BCD display. These ones are actually pretty expensive with respect to buying the LEDs. So yeah, there's always a way to cut on costs. Just place this back in, and it will clip. Just you need to push these little clips back in. There you go. So that was a little insight on the display here. Okay, so I will, to run a short test, I will wire it up and be back. Okay, so we're back. I connected the electrodes here, plugged in my say 5000 milliamp Rhino 50C discharge. This is not so new. It has already, I think, over 2.5 years, 3 years, and it's a little bit bulgy, but it still delivers what it needs to. I also have another one, a graphene one, which is a monster, so I don't usually use that. It's over 7,000. This one is more than enough for testing. Now, this purple spot welder, this KEKK K100, has more options than the smaller one, this other one. This one, you set the time, and basically that's all you can do, the delay. This one gives you a lot more information and is a little bit more sophisticated. It has, you can program the delay, and this is a DLST, it's the weld delay. Then you have the first, because it's a multiple, it's a double weld algorithm, which is actually good. This is the first weld millisecond time. Then you have the interval between the first and the second weld. This is 10 milliseconds. And this is the second weld time. Then you have the input voltage, which I checked. I think I just checked because I was like, wow, it's a little bit low. But to be honest, if you check with the tester, I don't know if you can see, the voltage. Yes, you can. It's 11.36, but it says 10.7. So yeah, that's about over 0.5 volt discrepancy. Okay, so anyhow, it shows you a lower voltage, which is better than showing a higher voltage. So okay, 10.7 is it's okay. I mean, you just need to know, better check it. And then you have the temperature. There's a little probe NTC somewhere here, and probably around the FET sides, close to this area here. Don't know if it's one of these components. I will check. And then you're back to square one. Now, I bought the bare bone one, and it goes without saying that you have to be very careful to isolate this PCB, because, you know, if you drop something on it, it's going to be a disaster. Like a little piece of any metal, you know, a strip, a part, anything that will fall into or create any small short circuit, that can be devastating. So yeah, I'm doing this now for testing. I did put a rubber pad here on the back with some double adhesive tape to isolate at least the back side. But yeah, always cover the PCBs up and make a print, maybe a little 3D box. I mean, with a 3D printer, print a little box or find a little plastic box where to put it in, and you know, keep this area protected. You can even just put it, make a little wooden box or something, but this thing has to be, you know, well out of shorts or fillings or metal parts away. So I'm going to start with a low setting, and I suggest everybody else does this too, especially when you're trying any welder for the first time and you're not sure of the parameters. Start with a couple of milliseconds. In this case, I have 3 milliseconds for the first weld and 5 milliseconds for the second. So it's pretty low, but you get an idea of how this thing works. I have two little strips. These are I think they're 0.1 or 0.12. Doesn't really make a major difference because this is 0.12, but I will check later. These are coming directly from batteries and stuff that I've used to do some tests. So I'll just place them here on a flat, hard surface. And let's try to weld this. These are, I think these are new. These contacts here they're very sharp on the edge. So when you weld and you're like this, you're gonna have a very small contact surface. So that's gonna, you know, probably burn through easier. But you're gonna get a smaller surface. You should be rounding these off slightly. Not a lot, but you know, I show this also in my other videos. So check them out. You know, just try to round the little surface just a little bit. I have I have some other ones I will show you probably later, but these were the new ones, so I'm just using these. So let's check this out. Okay. That was, you see it got stuck, so yeah, current is I just did one weld here on purpose. I want to see how it performs. Okay, well, welded, it seems to be welded because it's very, very stuck. Now, to test a weld, you can slowly rip it off, but instead of being violent, just try rocking it. And that way you will see, especially if you feel it there. You see it came off. Don't know if you can see it, but the two welds were here, one here and one here. And you see that lighter area? And that's some nickel peeling. I'm gonna squash this. Yeah. Yeah, it came from there. You can squash this back. Yeah, there's also a hole. I don't know if you can see it. So it did puncture it, meaning that the weld it went through. That's okay. We can, I would suggest, let's see, 3 milliseconds start weld. Why not? Let's increase the second weld to 8. Step by step. And we'll do it in a new area. This one is clean. And when you're welding, be careful to weld on clean areas, meaning that these have been soldered on. Don't weld where you have solder. That will cause a lot of splatter, and it's not really nice. I'm going to stay away from the solder side. So I'm going to stick here one and the other one here. Let's see. Okay. You don't see on the underside, you should see some discoloration. There's slightly there and there. You can see it. Don't know if it comes through the camera. I'm using low values on purpose, but already you can see that the welds are. Let's try to do this without ripping it, because I want to remove it without. And you can check the surface. Because if you rip it all up, then you can't really see what happened in the middle. And if you do it carefully by rocking it back and forth, you can sometimes get it to detach. Maybe if it's like on the surface, you know, the nickeling. There, you see I'm rocking it, zigzagging it, and it will break at a certain point. The weld is good, I'm just, yeah, there. So now you can flatten it again and check. You see there's a puncture here, and there's I don't know if it's punctured or not on the bottom, but the fact that it went through demonstrates that the weld is complete. I mean, it's a good weld. And here's the upper part. I don't know if you can see it. This is the part that remained on this side of the strip. And yes, you can also see that it's punctured here too. So yes, I can definitely say that even with a small, I mean, the settings are 8 milliseconds is the second weld, and 3 milliseconds is the first. Usually, you start by giving a short first pulse. That will kind of heat up the two contacting areas, and the temperature will rise pretty high. I mean, we're already talking about a few hundred degrees. And then when the big pulse comes, that will definitely fuse it. So double pulsing is important, and it will actually, you can actually weld better with shorter pulses, being a double pulse. I wouldn't be able to get this performance with these small strips. You see there's a hole. I don't know, but you can see that they are punctured, so that went through. You wouldn't get with an 8 millisecond pulse with this one. You wouldn't get that performance. I would need to go up at least to 10 or 12 to puncture these, like I did with this one. So the performance, the algorithm is very, I mean, it's a good, okay, it's a good good way, definitely good price to quality ratio. I mean, considering, you know, that you, okay, the slight mod that you do here, it takes you what, 5 minutes, 10 minutes, you know, cut a track, put a piece of wire, solder it there. Once you've done that on this version, if you already are lucky enough to get the already modded version, and you can check that with that track, I will put a picture up when when I edit it, so you can see the difference. Then you're fine. You don't really need to do anything at all. That's all. You just need to experiment and check how your strips are behaving between the first and second pulse. The delay between the first and second pulse shouldn't be too long, because then you're losing the effect. You should start with a short, I think this was already 10 milliseconds because I didn't really touch anything here, which is okay. You can try shortening it. The concept is that you keep the temperature of the first weld high enough so that the second weld will kick in at the correct temperature. If you wait too long between the first and the second weld, you're actually nullifying the double spot weld. It really depends on the total amount of energy you're putting in. If you're doing much larger welds, I mean with thicker strips, you might need to wait a little longer, but that's it really depends on the material. I'm using this block here because this dissipates a lot of energy, so it's like a lot of heat. So it really cools down the weld quicker than doing it, for example, on a battery, because the thermal capacity of this battery is of course less than this aluminum block here, which is on purpose. And you see when things fly around like this, you have to be careful, because if one of these strips were to fall on the circuit board, it may be disastrous. So that's what I was talking about. So yeah, this is a classical 18650. I don't know, it's one I recovered them from old server parts. The controllers have a onboard, smart controllers have an onboard cache backup system, so that, you know, if you have a energy blackout or something, you do save the contents in the cache, and when the energy comes back, when the electricity comes back, the cache can be then dumped and written to the disks safely without corrupting anything. And usually what happens, these are in HP and also other servers, other branded servers, they come in couples, and somehow the electronic balancing system, it stops, and when one of the two cells, they are charged and controlled separately, when one of the two cells drifts too far apart, they just stop charging and they flag an error, and you have to replace them. There's no way. If you catch this before, then you can replace one battery and kind of like trick the controller that it's still okay, and it won't block it. Otherwise, once it determines that it's failed, you're doomed. You can't even replace the batteries. So what I do is I remove the packs and test them, and usually one of the two cells are still good, so I use it for something else. This one, which is kind of good, but it was, I think, one of the bad ones, I keep it for testing. And these come with very, very thick strips. They are, I think, 0.2 millimeters. I've ripped this off now. Like this one here. This is an old nickel cadmium battery cell. These are actually 0.12 millimeters, but these are connected with each other with these thicker strips. Now, these thick strips here, these are machine spot welded, and they are very, very tough. If you look at how they're spot welded straight, meaning that the electrode is placed on top like this. However, it's smaller than this. It has a tapered flat point. And you can see that because the weld is circular and it has a little bump in the middle. And yeah, you have to be careful when you're welding like this, because if you do not calibrate it correctly, you're going to perforate the cell. The thickness of these cells is 0.3 millimeters, so that's not a lot. People often forget that. And if you have a 0.2 millimeter strip and you want to weld it on here, you have to be careful, because it's easy to go over the temperature of the fusing point of the cell container itself, and then you're going to make a little puncture. And if you don't realize that, in a couple of months this cell is going to be dead, if not dangerous. If you have a humid environment and it starts leaking, this thing can even heat up. So it's not always a good idea to go with very thick strips. Just a word of warning, because I've seen people insisting on going over 0.2 millimeters on cells like this. And yeah, beware of that, because the thickness of this cell is not what you think it is. It's 0.3 millimeters. If it's in specs. If you get some Chinese clone, it may be even less, so be careful. The reason why these have to be that thick is for pressure and containment purposes. These have a protection, let's say cap, which is under here. This is a fake cap. There's actually nothing under here. There's a little protection fuse. The real cap is here, where it's crimped. Now, what this does is if this goes over pressure, it will blow open, release the pressure, which vents through these openings, and that will save you a lot of aggravation, if you know what I mean. Anyhow, so beware when welding any kind of these cylindrical cells, not just the 18650s, the 217, any kind, there is a limit. And factory spot welding is done by calibrated machines. So yeah, this has been tested on several thousand units. But when you're doing it by hand, there are so many variables, meaning that the power source is different, the points are different every time you weld. You're never positioning it the same way because you're a human and you're not a machine. So every time you do weld it, everything is different. That's why you know, when you're doing it for hobby reasons, it should be done within certain limits. Do not exceed, I mean, my suggestion is never exceed 0.2 millimeters thickness, because it will start getting dangerous, not just for the weld itself, but in time your battery may have some lesions and you are not aware of it. So yeah. The top side is actually easier because if you look, it's separate, right? It's like there's a separate cap. It's not in contact with the battery itself. So this area is actually easier to weld because the temperature of this cap will rise much quicker, having no contact, right? It has a very small thermal capacity. Now, if you do puncture this cap, nothing really happens. The problem is puncturing the container. This is the container. Another thing which you should be looking out is if the battery, no, not in this case because we have some strips here. I haven't removed these because if you do attempt to remove them, you can puncture the battery. These strips are spot welded very, very well, and they're fused with the container. If you try to rip these off, you may puncture the container. Do not try. Just cut them off like I did here at the strip. You bend it a little bit, and that's it. They won't give way that easily. These things are incredibly well welded. You do not find these typically on cheap Chinese battery packs. They are welded. You probably will weld better. These are professionally welded in factories which have a very high quality standard. I mean, we're talking server machines, certain maybe laptops. So they come out of a different quality production check. And you know, when you're talking about e-bikes or stuff like that, that's a whole different ballpark. So, I mean, based on the costs they invest for creating the packs and you know, the liabilities, etc., etc. So I didn't want to make this thing too long. It's already been an hour. Let's see. I will see if maybe we can try welding this strip, which is a 0.12. I don't know where my caliber is. Maybe on this side, because this one has already a weld here. So maybe I will try, or I can try anyhow on this side and see what happens on a real battery. Okay, it's just one weld. I don't want to exaggerate. If you check, you can see that there has been perforation here because you can see it. Yeah. Now let's lift this, and I do it diagonally because it's easier for the weld to rip off. So you do go like this, you don't pull it, and you start zigzagging it up and down. You can lift this side too, slightly, so you can give it some room. So it's a V like this, and you simply rock it back and forth. Okay, you can feel that the weld is there because even if I'm rocking it, the other side is not rocking a lot. Okay. Thing is out of focus. Okay, so now I'm going to try to rock it more. As you can see, it's very hard to even detach it like this. But once it starts moving, very slowly, this is how I get off also other spot welds, the ones which I don't want to ruin, you know. See, I'm moving this side and the other side is barely moving. It means that it's pretty well welded. And it's not coming off, though you can see that there is a hole already. You see the light coming through? So definitely with such a setting, I mean, I have 3 milliseconds and 8 milliseconds. So the longest weld here is 8 milliseconds. And yeah, it's pretty well welded. Yeah, I'm surprised. Okay, it's come off. And now the other part is going to come off. Okay, I detached it. You can see that one part is still there and the other part is also on this side. And the demonstration is the fact that if you look through, you will see holes in the strip. I don't know if you can see them, but there are 2 holes. So that means that that part of the strip has been transferred to the battery cap and it's there. It's actually here. You can see one is right here in the corner. You see? And the other side is here. So yeah, I wouldn't go over 10 as a second weld contact, and I would keep the first one 3 milliseconds. It's more than enough for this. For my setup, I mean, with my battery and this thickness here. This is 0.12, the strip here. And I believe these are 0.1. Or these are 0.12 too. I mean, I need to check. It's not a real big difference anyhow. This is a brand new strip. You can also try, let's see. Yeah, this is 0.12. Let's see. I can try from the back, but unfortunately I have not a lot of surface here. I can't weld on top of these. You can try welding here. Let's try this. Okay. Same setting as before. Okay. Sparks flying means that there is material being ejected, which can be either dirt or oxide or material nickel. And yeah, definitely again a good weld. You can bend it. I can't lift it in this case because I put it against these old strips. But if you pull it away like this, let's see if maybe I can try. Yeah, and there's another puncture. Yeah, this one is breaking off too. Okay, you can see the 2 welds there and the holes here. Okay, and there's just 2 welds and small surface but good weld. If you do 4 of them, 2 couples, you're fine. You don't really need super deep welds here for normal projects. And if you put your hand on the surface, you can feel the nickel, the part of the nickel strip that's welded here and here. You can actually, yeah, it's welded. So with this minor setting, you're already getting good welds. This is another battery, nickel cadmium. Actually, these are very long lasting, and 2 couples of welds don't remember if I did this many years ago with another machine. Possibly. Let's try here with the same strip, or even this one. This one I removed from a pack. I think this is also 0.12. It should be the same. Okay. Put this in the corner here. Put this, I will zigzag this. Okay. And it sticks pretty well. Yeah, these are sharp edges here. So there's the weld. You can see that it's actually, also this one has gone through pretty well. Now I'm going to try to peel it off, zigzagging. It's already, if you look, it's already formed. That means that it's transferred. So yeah, this one is also, yeah, that setting is pretty good. Let's see if I can rock it off. Okay, whoops. Yeah, you can see definitely can see the two spot welds here. Don't know if you can see them, 1 and 2. And well, I exaggerated by pulling this time and I ripped it off, but you can see that they've both punctured again. It's a small puncture, but it's there. So yeah. What can I say? I mean, after this mod for this version, definitely a good cheap welder. Better, certainly better than the simpler ones that have no double pulse. I mean, this is a firmware issue. You could actually reprogram this to support the double weld, but yeah, nobody will do that. This one has it, and if you have to choose between the two, go for the KEKK. If you're lucky, you're gonna get the one that already has the mod. So you're set. You're all set. You just need to plug in and play, plug and weld. And if not, you just a little piece of wire, cut this trace, and yeah, you're good to go. You have no major issues there. It's fine. Cover it up, please. If you can, buy the kit with the plexiglass covering like this, because it's much better. And also you can maybe, if you have a 3D printer, you can 3D print your own box, or just find any plastic container with an opening here with a little plastic, transparent or something, and so you can actually press it. But actually, all you need to do is find the right settings, then you can close it up and just weld. That's all. It still says 10.7. Okay, that is. Good thing is also the junction temperature, but yeah, I mean, I just did couple of welds. After like 10 welds or so, usually you can start feeling that this part here gets warm. That's normal. I usually don't do a lot of welds in a row because, I'm not I don't make hundreds of packs. I just fiddle around with what I have and change and other stuff. So I don't really use them intensely. I just like analyzing and doing some tests, and when I need to do some other packs, I do. But it's usually smaller stuff like laptops or things like that. Okay, so I hope you enjoyed this video, and if you have any questions, just put them down in the comments. I think I covered everything. If you want to have any more like details on this, generally on welding or on the issues that there may be, check out all my prior videos. Feel free to subscribe, because that also helps the visibility of the channel. I see that there are moments that I get like a lot of views and then suddenly much less. Depends, I really don't get it, but I guess I see that most of the views are from non-subscribed people as usual, like 80% of the views. So I don't usually post often, so it's not like it's gonna be, you're gonna be spammed by new videos, but at least that when I do, you know about it, and that actually helps everybody else. So yeah. I will. I wanted to do something. No, I think that's about it. If I recall anything, I will write it down or add it at the end. So have a good weekend or week, everybody, and I'll see you next time.